All right, so here we go. This is our video for section 2.2, which is about just overview of what functions are, and then analyzing graphs of functions. So the first thing, just reminder of what a definition of a function is. So a function is a relation where for every input there is exactly one output. And one way you can think of functions are with these little set blobs. So if we think of the input values as our domain, let's say that these 5 numbers consist of our domain, and then we have an output values, which is our range. For every input, it's mapped to exactly one output. So 1 is mapped to 4, 3 is mapped to 7, 5 is mapped to 7, 7 is mapped to 13, 9 is mapped to 25. So each input only goes one place. Now, it's okay if you have 2 inputs that are being mapped to the same output. It's still a function. It doesn't violate this definition. So then, because of that, we have the vertical line test for functions. And the vertical line test just says if it is possible to draw a vertical line on a graph that intersects the relation in more than one place, the graph fails the vertical line test, and the relation is not a function. So here's a graph right here, which turns out to be a function. There's no place we can draw a vertical line that's going to intersect this in more than one place. Same thing with the second graph. There is no place you can draw a vertical line that will intersect in more than one place. Sorry, I should say more than one place. The third graph, though, as long as there's one place where you can draw a vertical line that intersects the graph in more than one spot, it fails the vertical line test. Now, it turns out I could have drawn that vertical line anywhere, almost, and it would have crossed in more than one place. But here's 3 places. It's more than one place, not a function. And you can kind of see how this vertical line test works. So because these 3 points are vertical from each other, they all have the same x-coordinate. But they have 3 different y-coordinates. So this one x value is mapped to 3 different outputs, and that violates the definition of a function. So that's how the vertical line test works. Now we have something called piecewise functions. And so piecewise functions, it's like the name sounds, they're functions that are in pieces. And so you can see that we have these 4 different pieces, but all together they make up one piecewise function. So it's kind of weird. So this is what a graph could look like. And so how do you actually write an equation then for a piecewise function if they have these 4 pieces? Well, let's take a look. So let's look at them piece by piece. So this piece right here, this first one, it's part of a horizontal line. And it's a horizontal line at y equals 4. So that first piece is part of the equation y equals 4. The second piece, if you pay attention to the points, it's actually a parabola, and it's the parabola y equals x squared. So if you take a look at these 4 points that are on there, this point is at negative 2, 4. This point is at negative 1, 1. This is at 0, 0, and this is at 1, 1. So each one of those 4 points, the y-coordinate is x squared. So it's the graph y equals x squared. The third piece is another horizontal line, but this time at y equals 3. And the last piece is a diagonal line. It looks like it's got a slope of up 2 over 3, so 2/3. If I continued that pattern backwards, it would intersect at negative 1, so that's y equals 2/3 x minus 1. Now, this is not the equation for the piecewise function. It's 4 different functions right now, the way it's written. I need to combine these together into one function. So what we actually do is, rather than saying y equals, y equals, y equals, y equals, we bracket these together and say y equals. Or you can also say f of x equals. But that's still not enough, because there's nothing yet that indicates, okay, the first piece is y equals 4, but only this piece. How do we know which part to draw? So the way we do that is we define the domain that that piece is on. So for instance, this first piece, remember domain is x values, so this first piece lines up with this part of the x-axis, where x is less than -2. So we say if x is less than -2. Now, we do have a solid circle here, so we actually want to include -2. And hang on, I actually want to get rid of the yellow part. Let me put that back now. If x is less than -2, and because we want to include -2, we'll put the equal to. And that's what we're going to do on all of these 4 pieces. We're going to go ahead and define the domain that it's in. So the parabola is sitting right there between -2 and +1. So we say between -2 and +1. Now, we have this thing right here, though. It's also a solid circle at -2 for the parabola. So you may be thinking, okay, so we'll put it equal to here. And although, I mean, it's kind of, in a way, correct to do that, because this point is part of the line and it's also part of the parabola, so why not include -2 in the line and in the parabola? But we just don't do that. It's not good form. So pick one. When you have a choice, pick one to put it in, but only put it in one. So I'm actually going to get rid of the equal to on the second one. But you only want to put it in one. It's just, think of it just like, instead of saying 2x, what if I said x2? Ooh. Hopefully x2 is just making you really uncomfortable. It just doesn't sound right. We don't do that. It's the same kind of thing here. Whoops. We just don't do it. It's just weird. So only if you have a choice of where to put a point, pick one, but don't put it in both. So then, if we get to the other horizontal line, that one is on the x-axis between 1 and 3. So, between 1 and 3, and we include the 1. And the last part is where x is greater than 3. So we say x is greater than 3, and it's not a solid circle, so we won't include it. And then this whole thing is the equation for one piecewise function. So it's kind of weird. It looks like, wait, there's 4 different things there. No, there's 4 pieces for one function. And that's writing the equation of a piecewise function. Okay, so then let's just do a little review of function notation. So function notation is this f of x thing. And remember, it is pronounced f of x. You don't say f times x. And just remember, like, whatever's in the parentheses, that's what gets placed in x. That's what you substitute x with. So if f of x is 2x minus 7, f of 3 means replace the x with a 3. And in this case, you evaluate, you get -1. For this guy right here, you can actually substitute in an expression. There's no rule that says you always have to have a value. So what if g of x is x squared plus 7? What's g of 2x minus 3? Well, that means take that x and replace it with 2x minus 3. So instead of x squared, it's 2x minus 3 squared plus 7. And then I just went ahead and squared this and added 7 and got that. If you have a piecewise function that you're going to evaluate, then it's actually still really easy. So we have this one piecewise function. Let's say I want to evaluate h of -3. Well, what you do is find the interval that the input lies in and substitute into the corresponding piece. So -3 is in this interval. So we're going to evaluate in this piece, we get -7. But if I want to find h of 0, 0 lies in this interval. So I plug it into that x, and I get +9. And that's how you evaluate a piecewise function. And then just a little reminder about some vocabulary here. X-intercepts, zeros, and roots are used pretty much synonymously. They're not quite the same. X-intercepts are referring to graphs, zeros, and roots. They can be for graphs or functions. Kind of weird. Anyway, people use them interchangeably because they pretty much are. Zeros and roots really are synonyms. They are exactly the same. In fact, on the TI graphing calculators, there is a place where you can ask it to find the zeros of the function. And the previous versions of the calculator, it used to say roots of the function. They mean exactly the same thing. And remember, to find x-intercepts, you let y equal 0. To find y-intercepts, you let x equal 0. All right, now another little concept here, handy one. Remember, if you ever want a fraction to equal 0, it will only equal 0 if the numerator is 0 and the denominator is not. So if we say find the zeros of this, remember up here, zeros are x-intercepts, and to find the x-intercept, you let y equal 0. So if I let y equal 0, now I want to know where the fraction is 0. It's all about the numerator. So I find where the numerator is 0, and I factored this, and I got my two values, and neither one of these values also makes the denominator 0, so these are the zeros of the function. All right, so then we have this idea of increasing, decreasing, and constant. So what does this all mean? Well, it's actually not that hard. You guys probably already know what increasing, decreasing, and constant is. You could probably tell me right now where the graph is increasing, decreasing, and constant. It's just how do you write your answer? But we can look at this graph and see that the graph is increasing, then it's decreasing, then it's constant, then it's increasing, decreasing, increasing, decreasing. So the way you write your answer, if you want to say where the graph is increasing, decreasing, or constant, it's all about the domain values, all about the x values. So the graph is increasing from -infinity to -5 on the x-axis. Remember, it's all about the x-axis. So from -infinity to -5, the graph is increasing. Then from x equals -5 to x equals -3, the graph is decreasing. Then from x equals -3 to x equals 1, the graph is constant. And then from 1 to 4, it's increasing again. And then from 4 to 7, it's decreasing. From 7 to 10, it's increasing. And from 10 to infinity, it's decreasing. And when you have more than one interval, you connect it with the union symbol. And so that's how you write your answer. Now the one thing, never include the endpoints, because by definition, we say that the graph is increasing on every point in this interval because just to the left, like if we take any point in this interval, just to the left of that point is smaller and just to the right of that point is bigger. So what do I mean by that? If we try to include -5 in that interval, if we try to put a bracket instead of a parenthesis, so if we're trying to say that the graph is increasing at x equals -5, then that means just to the left it was less, and just to the right it was more. It's going up, but it's not. Just to the left it's less, but just to the right it's also less. It's also lower. So it's not increasing here. At this point A, it's still increasing at A, because just to the left it was lower, and just to the right it's higher, so we're still going up. But we're no longer going up at -5. So That's why we never include the endpoints on these intervals. So that's increasing, decreasing, and constant, but what's this extrema? So what the extrema is talking about is minimum and maximum values. And we have 4 different kinds of extrema. There's relative minimums, and actually sometimes they're called relative, sometimes they're local. Just depends on who's speaking. And honestly, I tend to, oh my god, I wrote relative twice. Sometimes I use them interchangeably too. I haven't picked one. So we have relative minimums or local minimums. We have relative maximums or local maximums. And then we have something called absolute or global minimums. And then we have absolute or global maximums. And these are our extrema. So what are these points? Well, a relative minimum or maximum or a local minimum or maximum, it's local. Like in that neighborhood, it's the highest point. So for instance, point B, just in this little area, B was the highest point. So we say that B is a relative or local, oh my gosh, sorry. B is a local maximum, not a local minimum. So think about what other points, if there are any, are local maximums. Let's look at maximums since we're on that topic. And hopefully you saw 2 others. Point E and point G were also relative maximums. And again, like the actual definition of a relative maximum talks about it in an interval that contains that point, every point on either side is lower than that point. So for a relative minimum, we have point F. But we actually don't call C and D relative minimums. It's kind of weird. But again, it has to do with the fact that just to the left of point C, there are points bigger, but just to the right of point C, there aren't points bigger. So we don't call that a minimum. That's not a point where there's a minimum. Then we have absolute minimums and maximums. Now, absolute, it's like of the whole graph. So in this whole entire graph, our maximum value happens right here at point E. In the whole entire graph, where's the lowest point? Well, there is no lowest point. It goes forever on either side, so we actually say there is none. And that can happen. So that's extrema. The last thing is symmetry. So let's first look at the kind of symmetry we're going to be talking about. We're going to talk about symmetry of something called even and odd functions. Now, there's other kinds of symmetry, but we're just going to look at those 2. So if we have symmetry about the y-axis, so let's take a look. If we have a point A, and we're going to reflect it about the y-axis, then it comes over here to A prime. And what ends up happening is the x-coordinates just change signs. If it was a positive x-coordinate, it's negative in the reflection. If it started negative, it's going to be positive in the reflection. But the y-coordinate stays the same. If you have symmetry about the origin, first of all, what does symmetry about the origin even mean? That's just weird. Well, here's a way to think about it. So let's say I want to reflect point B about the origin. Like, how do you reflect about a point? Well, imagine starting at point B and then drawing a line to the origin and then continue that line for the same amount of distance. And that'll take you to the image. That's how you reflect a point. So this line segment is the same length as this line segment. Now take a look at what ends up happening to the coordinates then. The x-coordinate changed sign and the y-coordinate changed sign. And this actually has the same exact result as if you did a 180-degree rotation about the origin. So if you actually turn the graph upside down. That's called symmetry about the origin. Now what does that have to do with even and odd functions? Well, even functions are functions with y-axis symmetry, and odd functions are functions with origin symmetry. So what does that mean? Well, the way to think about it algebraically, again, thinking about this graph, a y-axis reflection just negates the x. So if you negate the x-coordinate, the y-coordinate doesn't change sign. That's an even function. The x-coordinate changes sign, but the y-coordinate doesn't. My cat says hi. Now for origin symmetry, if we change the x-coordinate, the y-coordinate also changes signs. The x-coordinate changes signs and the y-coordinate changes signs. So even functions are when f of negative x equals f of x. Odd functions are when f of negative x equals negative f of x. Okay, but what does that mean? Well, let's take a look at this example. I'm going to go ahead and leave those two definitions up there. So let's say we want to determine if the function is even, odd, or neither, and we're given f of x equals 3x squared minus 8. We'll look at both of these definitions. Both of them start with f of negative x. So we're going to replace x with a negative x and see, do we get the original function back? Then it's even. Do we get the opposite of the original function back? Then it's odd. If we can't get either one of those, it's neither. So let's take a look. So if I take this blue function, f of x, and I substitute a negative x in for the x, this is what it looks like. Now let's try to simplify it. Let's see what happens. A negative raised to an even power will be positive, and a positive times 3 is positive. And so I wind up with this, but hey, that's just the original function. So I wind up with f of x. So f of negative x is f of x, so it's an even function. Now let's take a look at another example. Let's say I started with this function instead. I'm still going to start with f of negative x. I'm going to replace the x's with a negative x. And a negative to an odd power is going to be a negative. And a negative times 4 is negative 4. And then a negative 7 times negative x is positive 7x. This does not look like the original function. But if I factor out a negative, look at what I'm left with. The original function. So I have the opposite of the original function, which makes it an odd function. So that's the idea. To find out if something is even or odd, you work with f of negative x first and see what happens. Can you simplify what you got to the original function, it's even? Can you simplify what you got to the opposite of the original function, then it's odd? Now, it's kind of weird if you think about the terms even and odd. Where do we even get those words from? Why would they call these even and odd functions? Well, you might be seeing it right now. If you are dealing with polynomials, now this only works for polynomials. And polynomials are, they're things like this. The coefficients have to be real numbers, so you can't have I. And the exponents on the variable have to be non-negative whole numbers. So they can be 0 or positive numbers, positive whole numbers, but no negatives, no fraction exponents, no decimal exponents, no square roots in the exponents. They have to be whole numbers. But that's what both of these were. The variables on the exponents were positive whole numbers, or 0. And notice when all the exponents on the variable are even, it's an even function. When all the exponents on the variables are odd, it's an odd function. And that will always happen with polynomials, and that's where they got their name from, even and odd. But it's only with polynomials. So we have one more example that we're going to look at, and that's this one. Same kind of thing though. Let's determine if it's even or odd or neither. So this is the function in blue that we're given. So we're going to start with f of negative x, replace all these x's with a negative, and we wind up with this. So let's see what we got. We have a negative cubed, which is negative, and a negative times a positive 4 is a negative 4. And then positive 5 times negative x is negative 5x. And then a negative raised to an odd power is negative, times 6 is negative 6. Positive times a negative is negative. Doesn't look like the original function, but if I factored out a negative from the top and the bottom, we are beginning to get the original function. And these negatives both cancel out, so we actually just have the original function. We just have f of x. So that's the definition for an even function, even though all of our exponents were odd. So be careful about using that rule of, oh yeah, the exponents are all odd, it's an odd function. It's only for polynomials. Otherwise, you gotta show your work and do all of this. And there you go. There is the first day's lesson in a nutshell. In a 26 minute nutshell. All right, have fun. Bye.